Hello, this recording is for Algebra 1, Chapter 7, Lesson 4, More Multiplication Properties of Exponents. This should be another relatively short lesson. This should be review for most of you. So let's talk about raising a power to a power. It's the same as raising the base to the product of the exponents. So here's an example. We have 5 to the 4th to the second. So 5 to the 4th is being raised to the second power. So that's what we call raising a power to a power, because 5 to the 4th is a power, and then, 5 to the 4th is a power, but then 5 to the 4th to the second is also a power. So what you can do is you can write it out in expanded form, which would be 5 to the 4th times 5 to the 4th, because the 2 actually applies to the whole thing there, which means we've got 5 to the 4th 2 times, but 5 to the 4th times 5 to the 4th is 5 times 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 5. So that would be 8 5s, but you can do it a little easier if you just know that you can multiply the exponents. So it would be 5 to the 4 times 2, which is 8, which is 5 to the 8th. So again, you can write it out in expanded form, or you can do it the easy cheesy lemon squeezy way, but you need to know that that's what this means. Okay? All right, next problem, we have t to the second times t to the 7th to the negative second. So just remember that exponents kind of act like distributive property, and they only affect the thing right in front of it. So if it's parentheses, it affects everything inside the parentheses. If it's not, like this, only affects the thing directly in front of it. So let's go take care of the power to a power first. So we have t to the second times t to the 7th times the negative second, which is negative 14. So we end up with t to the second times t to the negative 14th. Since the bases are the same from the previous video, we're going to add the exponent. So it's going to be t to the negative 12th. All right, there you go. All right, next problem, we have a to the 4th to the second times a to the second to the 5th. So again, we're going to multiply the power to a powers. So that's a to the 4 times second times a to the second times 5th, which is going to give you a to the 8th times a to the 10th. Since the bases are the same, you can add the exponents. So that would be a to the 8th plus 10th equals a to the 18th. Pretty easy, right? Okay. All right. So what if we are raising a product to a power? So basically, if the thing inside the parentheses is also being applied by the power, which I think we've already done. Nope, no, we haven't done that yet. Okay, so so if we distribute, we're going to treat this kind of like distribution. So basically, this means 3x to the 4th is really 3x times 3x times 3x times 3x, 4 times. So then you would just do 3 times 3 times 3, which is basically 3 to the 4th, and x to the 4th. Whereas opposed, you can just go ahead and distribute. So if, oops, I forgot to add some stoppage in there. So again, the other way you can do it is just distribute. So it'd be 3 to the 4th and x to the 4th, which is what we have right here. And then if you actually do 3 to the 4th, again, you're going to get 81x to the 4th. Okay, so the next problem, I did a lot of work without stopping. Okay, so again, we have 4g to the 5th to the negative second. And again, you can distribute the negative second to everything. And again, since this one's going here, it kind of acts as a group. All right, so we're going to have 4 to the negative second, and we're going to have g to the 5th to the negative second. Well, g to the negative second is 1 over 4 to the second, which is the same as 1 over 16. Now when we talk about the g to the 5th to the negative second, we get g to the negative 10th, which is the same as 1 over g to the 10th. Because remember, the negative tells you to move that power to the other side of the fraction bar. So if you have a negative on top, it goes to the bottom and becomes positive. If you have a negative exponent on the bottom, it moves to the top and becomes positive. Again, the negative just tells it to move to the other side. No matter which side it's on, it just moves to the other side. So now we have 1/16 times 1 over g to the 10th, which is, when you multiply fractions, 1 over 16g to the 10th. And you could also write it as like 16 negative 1 g to the negative 10th if you were to write it without an without a fraction bar. But most people like to see positive exponents whenever possible, so that's why this is the preferred answer. Okay, so more than one power raised to a power, and then you just simplify the expression. So again, I didn't put enough breaks in there. So again, we just have a lot going on here, but just remember the exponent kind of gets distributed. There we go, something like that. All right, so again, the 5 is going to go to the 2 and to the a to the 3rd. And so we have 2 to the 5th times a to the 3rd to the 5th, which is the same as 3 times 5. And then we have an a to the 3rd, or a 3 to the 3rd, an a to the 3rd, and a b to the 2nd to the 3rd, which is again the same as b to the 2nd times 3. So if we go ahead and simplify it, like those arrows already showed, we're going to have 2 to the 5th, which is 32, a to the 3rd to the 5th, which is a to the 15th, a to the 3rd, which is, 3 to the 3rd, which is 27, and a to the 3rd and b to the 2nd to the 3rd, which is b to the 6th. Now let's go ahead and combine some like terms. 32 times 27 is 864. A to the 15th times a to the 3rd, add the exponents, which means it would be a to the 18th, and then we just have b to the 6th off on its own, which means if I write it without the multiplication dots, I have 864 times a to the 18th times b to the 6th. All right, next problem. Remember, we're going to distribute the exponents to everything that's inside the parentheses. We're going to end up with 6 to the 3rd, m to the 3rd, n to the 3rd, times 5 to the 2nd, m to the negative 3rd to the times 2. So let's go ahead and simplify some stuff. 6 to the 3rd is 216, m to the 3rd, n to the 3rd, 5 to the 2nd is 25, and we have m to the negative 3 times 2, which is m to the negative 6th. Now let's combine some like terms. 216 times 25 is 5,400. M to the 3rd times m to the negative 6th. We're adding the exponents because the bases are the same. That would be 3 plus negative 6, which is negative 3. And we just have the n to the 3rd. We write it without multiplication dots, and we're good to go. Alrighty. So let's go ahead and apply this to a word problem. And apply this also to scientific notation, actually. So the mass of a feather is 10 times 10 to the negative 5th kilograms. And we're going to simplify the expression 10 to the negative 5th times 3 times 10 to the 8th to the 2nd to find the amount of resting energy in joules the feather contains, because the weight or mass of the feather times 3 times 10 to the 8th to the 2nd will find you the resting energy. So it's 5 times 10 to, 10 to the negative 5th times 3 times 10 to the 8th to the 2nd. Basically, I just rewrote this with actual exponential notation at the superscript as opposed to the caret, right? So basically all I did was rewrite that. So let's go ahead and rearrange things. And just remember that 3 times 10 to the 8th to the 2nd can be written like this, because again, the 2nd means that there's 2 of them, all right? So since I know that there's 2 of them, I have 10 to the negative 5th times 3 times 10 to the 8th times 3 times 10 to the 8th. Well, combine like terms. 3 times 3 is 9, and since we're dealing with scientific notation, 9 is greater than or equal to 1, but also less than 10, so that can stay the way it is. And then I have 10 to the negative 5th, 10 to the 8th, 10 to the 8th. Since all of the 10s have the same base, I can add the exponents, which means negative 5 plus 8 is 11. It's not 14, it's 11. That's right. 16 minus 5 is 11. All right, so it is 9 times 10 to the 11th power. All right, last problem. The mass of a drop of water is 2.5 times 10 to the negative 2nd kilograms. Simplify the expression 2.5 times 10 to the negative 3 times 3 times 10 to the 8th to the 2nd, and then go find the amount of resting energy in joules the drop of water contains. Again, you notice how this number repeats and the problem before and this problem. That's because resting energy is dependent on this number right here. Okay, so we have 2.5 times 10 to the negative 2nd times 3 times 10 to the 8th to the 2nd. It's very similar to the last problem, but I'm going to do it a little different because I'm going to go ahead and distribute the 2 to this 2 right here. I'm going to go ahead and distribute it as opposed to writing it out in expanded form. The last problem I didn't expand it. This time I'm going to distribute. So we have 2.5 times 10 to the negative 8th times 3 to the second, because the second is going to go here, and then this is going to be to the second power. So times 10 to the 8th to the second. So let's go ahead and simplify. We have 2.5, right, times 3 to the second, which is 9, because 3 times 3 is 9, times 10 to the negative second, times 10 to the 16th, because a power to a power means you multiply the exponent, so it's going to be 8 times 2, which is 16. Go ahead and combine like terms. 2.5 times 9 is 22.5. The only thing is that's not in correct scientific notation, so I need to move the decimal place over 1. Since it was big and mighty, bigger than 10, it needs to get a positive exponent, and I only had to move the decimal place over once, so it's 2.25 times 10 to the first times 10 to the negative second times 10 to the 16th. All of those 10s have the same base, so I'm going to add the exponents, which is going to be 2.25 times 10 to the 15th, because 1 plus negative 2 plus 16 is 15. So it would be 2.25 times 10 to the 15th. Okay, I'm done. Bye.